Algebra 2, Section 3.3, Perform function operations and composition. Operations on functions. Let's let f and g be any two functions. A new function h can be defined by performing any of the four basic operations on f and g: addition, subtraction, multiplication, or division. Let's look at each of these using this example. I'm going to let f of x equal 3x squared plus 2 and g of x equal x minus 1. So to combine them with addition, it's as simple as just taking the 3x squared plus 2, adding it to the x minus 1, and then I just want to simplify by combining like terms. So I'd have 3x squared plus x, and I can combine the 2 minus 1, which would just be plus 1. So my new function, h of x, would be 3x squared plus x plus 1. Subtraction works in a similar way, but I need to be careful with signs. For subtraction, if I want to take 3x squared plus 2 minus g of x, now g of x is the whole quantity of x minus 1. So I'll put parentheses around that to remind myself that I'm not just subtracting the x, I'm also subtracting the negative 1. So when I combine like terms here, I would have 3x squared, nothing to combine it with, then minus x, and then this would be 2 minus a negative 1, which would become 2 plus 1, which would be plus 3. So you can see a slight difference there, but we got to be careful with the signs. Now for multiplication, I'm multiplying the quantity of f of x, 3x squared plus 2, times the quantity of g of x, which is x minus 1. And here I have a binomial times a binomial, so I would need to multiply that out using FOIL, or just making sure that I distribute each term in the first to each term in the second. So 3x squared times x would be 3x cubed. So that's first times first. Outer times outer, 3x squared minus 1 would be minus 3x squared. And then moving on to the 2 times x, so that's inner times inner, gives me plus 2x. And then last times last, or the 2 times the negative 1, and we get minus 2. Then I want to look and see if I have any like terms to combine. In this case I don't, so that is it. Now for division, we want to take f of x, 3x squared plus 2, divided by x minus 1. And I'm just going to leave my answer like that. I don't have any common factors I could factor out and cancel. Do not try to cancel x's here because they're part of a bigger thing with the addition and subtraction. And in the last chapter, we would do either long division or synthetic division to go ahead and divide it out. But in this case, I just want the value of h of x in simplified form. So just leave it like that. Now, another key concept we need to talk about in reference to these is domain. Now, you might remember domain is the input or the x values of a function. So as it says here, the domain of h consists of the x values that are in the domains of both f and g. Additionally, the domain of the quotient does not include x values for which g of x equals 0. So let's come back to our f of x and talk domain. With domain, you want to think first, well, what are you limited by? Well, we can't divide by 0, and we can't take the square root of a negative. Well, f of x is not dividing by anything, and it's not taking the square root of anything. So the domain for f of x is all real numbers, which I can use that R symbol for. Another way of thinking about this is that I could plug in absolutely any value for x and get an output. I could plug in positives, negatives, I could plug in decimals, I could plug in fractions, and I will get an output value. And the same thing goes for g of x. Look at g of x. I'm not dividing by anything. I'm not taking an even root of anything. So I'm not limited in the domain. Domain is, once again, all real numbers. X could be absolutely anything. So then for addition, when I combine those two, the domain is still all real numbers. And that's actually the case for these first three here. Because the domain of my original two functions was all real numbers, and I just added, subtracted, or multiplied them together, the domain is the combination of those two. And if I look at them individually as well, I can see in each of these, I'm not taking the square root of anything or an even root of any negative numbers. I wouldn't be able to divide by 0. So again, that's it. Now with division, we are limited here in the domain because I cannot divide by 0. So whatever's on the denominator cannot equal 0, which means here x cannot equal 1 because 1 minus 1 equals 0. So the way I'd say the domain for this one would be all real numbers except for 1, or x not equal to 1. Some of the functions we'll be combining will be power functions. A power function is a type of function which has the form y equals a times x to the b power, where a is a real number and b is a rational number. Here we have two power functions, f of x equaling 5x to the 1/3 power, and g of x equaling negative 11x to the 1/3 power. And we're asked to find the following. F of x plus g of x. So we look at function f of x, which is 5x to the 1/3 power. And we want to add it to g of x, which is negative 11x to the 1/3 power. And because these are like powers, x to the 1/3 power and x to the 1/3 power, we can just combine those by combining the coefficients. 5 plus negative 11 would be negative 6, x to the 1/3 power. Then for f of x minus g of x, that'd be 5x to the 1/3 power. Then minus a negative would become plus 11x to the 1/3 power. And 5 plus 11, we get 16x to the 1/3 power. Then we're asked to find the domains of f plus g and f minus g. Well, let's look at the original. The cubed root of x. Well, I could take the cubed root of a positive number or a negative number or 0. I could take the cubed root of a fraction or a decimal, so I'm not limited in the domain at all. Domain would be all real numbers. And same thing for this one. I'm not dividing by 0. I'm not taking an even root of a negative number. So x can be negative for the cubed root. So the domain here is all real numbers. So then when I add those together, I end up with a function whose domain is a combination of those two, all real numbers. And same thing for our next example, also all real numbers. Once again, I'm not dividing by 0 in either of those. I'm not taking the square root or an even root of a negative. So the domain's just all real numbers. Now let's look at combining two new functions, f of x times g of x. Well, f of x is 8x. We'll multiply that by g of x, which is 2 times x to the 5/6 power. And what you'll notice when we combine these, we're going to still be using our properties of rational exponents that we looked at in the previous section. So here, it's all multiplication, so I can multiply 8 and 2 together first because the order I multiply does not matter. So that gives me 16. And then I can multiply like bases. This would be x to the 1st power times x to the 5/6 power. So I want to do that by adding the exponents. 1 plus 5/6 would be 1 and 5/6, or 11/6. So it'd be usually best to write it as a improper fraction. And I get 16x to the 11/6 power. All right, now let's look at division. We have f of x, which is 8x, divided by g of x, which is 2x to the 5/6 power. Now in this, because I don't have addition or subtraction, I can simplify by dividing like bases. I also have this 8 divided by 2, which is 4. And again, I couldn't do this in the previous problem of division we looked at because it involved addition and subtraction. But here, this is factors divided by factors. So I can divide them in parts. 8 divided by 2, we got 4. This would be x to the first divided by x to the 5 6. And remember, dividing like bases, we subtract the exponents. 1 minus 5 6 would be 1 6. So I get 4x to the 1 6th power. All right, now let's talk domain. F of x, original domain, all real numbers. I'm not dividing by x or taking the even root of x, so that does not limit me any. Then the next one, here I have x to the 5 6th power. Now, because that's an even root, x is going to have to be greater than or equal to 0. Because if I try to take an even root of a negative number, that is undefined. Well, it's an imaginary number, which we're dealing with just real numbers here. So the domain for g of x would be all real numbers where x is greater than or equal to 0. So the original domains also limit any combination of those functions that we have. So I know that I'm looking at x has to be greater than or equal to 0, and I want to see if any additional things limit the domain here, which they don't. X would still have to be greater than or equal to 0 because I have the 1 6th power here, or 11 6th power. So my domain, all real numbers, x greater than or equal to 0. Once again, because if it's a negative value to an even root, that is undefined. And for our next one, because we have division, what's on the denominator, the 2x to the 5 6th power, cannot equal 0, which would mean if I solve that for x, that x cannot equal 0. So the domain for this one is all real numbers, now not where x is greater than or equal to 0, but where just x has to be greater than 0. 0 would not work because I'd end up dividing by 0, and any negative numbers would not work because I'd take the even root of a negative, which is undefined. Functions can be used to represent a lot of things in the real world. Here, in this example, a small company sells computer printers over the internet. The company's total monthly revenue, R, and costs, C, are modeled by the functions. So here's our revenue function, and here's our cost function, where x is the number of printers sold. Find R of x minus C of x. All right, so R of x is 120x minus C of x, so we would need to subtract the whole quantity of 2,500 and 75x. So if I simplify this, combine like terms, 120x minus positive 75x would give us 45x, and then minus the 2,500. And that is the revenue, the amount we bring in, minus the costs, the amount it takes to produce these printers. And next question, let's see, it says explain what this difference means. Well, that would be our profit. Anytime you take the revenue minus the costs, that gives you your profit, which would be the amount that you make after the costs. A composition of functions is plugging one function into another. So a function g with a function f, well, the composition, of a function g with a function f is g of f of x, where we're taking function f and plugging it in to function g. And we define that to be a new function of h of x. The domain of h is a set of all x values such that x is in the domain of f and f of x is in the domain of g. So we start out with function f, and the domain is the input of function f, and those are the x values that we plug into this function. Then the output of function f, which is f of x, is what we then plug in to function g. So that becomes the input of function g. And you might remember domain is the input of a function, range is the output of a function. So then what we do is f of x becomes the input of function g, so we plug it in to function g, and what we get as a result is the output of function g, or the range of function g. Let's look at some examples of compositions. Here we have two functions, f of x and g of x, and we're asked to find the value of f of g of negative 3. Now we always want, with compositions, we want to work from the inside out. So the inside says, find the value of g of negative 3. So look at function g. G says take the input and square it, then subtract 1. So our input is negative 3. We need to square it and then subtract 1. Negative 3 squared is 9. Minus 1 is 8. So this was our input of function g, and here's our output of function g. Now our output of function g becomes the input of function f. So now we want to find f of 8, and I look at function f up here, and it says take 3 times the input minus 4. So in this case, that'd be 3 times the input of 8 minus 4, which is 24 minus 4, or 20. So let's look at my options, and it looks like it does match up with option C there, being the correct answer, that the value of f composed with g at negative 3 is 20. Now, even if I don't know the input, if we leave the input just as x, we can still do compositions of functions, and we're still going to start from the inside and work out. So, to do f composed with g of x, or f of g of x, we can start by replacing g of x with what it equals. Well, g of x, I can see from up here, has a value of 4x plus 5. And then this says that for my function f, I want the input to be 4x plus 5. So I look at function f, and f says to take the input, raise it to the negative second power, and then multiply it by 6. All right, let me erase that so I can see a little better. So I want to replace x with 4x plus 5 in function f. So I have 6 times the quantity 4x plus 5 raised to the negative second power. And let's simplify that where I don't have a negative exponent. So the 6 will stay on top. It doesn't have a negative exponent. And then I'll write it as 4x plus 5 squared. And there's my function of f composed with g of x. So in example A, another way of thinking about this is that we started with function g and we plugged it in to function f. Now for B, we're going to go in the other order. We're going to start with function f, and we're going to plug it in to function g. So let's start with the inner function. F of x has the value of 6x to the negative second power. And then I look at function g, and function g says take the input, multiply it by 4, and then add 5. So 4 times the input, which is now 6x to the negative second power, and then add 5. Let's simplify that a little bit. Here I can take the 4 times 6, since that's all multiplication, we can multiply those together. Then I'd have x to the negative second, which I may write as x to the positive second, and then plus 5. Then let's look at C here, g of x. So we'll start out with, again, the inner function, g of x, which is 4x plus 5. Oops, that looks like a negative. Okay, as we look at domain, we need to consider the parts along the way as well. So with A, we start out with g of x, and when I look at g of x, x could be absolutely anything. So our domain would be all real numbers because I'm not ever dividing by a value of x, so I can't get divided by 0. I'm not taking an even root of x, so x can be negative. So g of x is fine, but then when I plug into f of x, it puts that on the denominator. And since we can't divide by 0, that means that the 4x plus 5 squared cannot equal 0, which would mean that 4x plus 5 cannot equal 0. And if I solve that for x by subtracting 5 divided by 4, x cannot equal negative 5/4. So the domain for f of g of x would be all real numbers, x not equal to negative 5/4. Then let's look at g of f of x. Well, at this point, that would be dividing by x squared, and x. So then the denominator cannot equal 0, which means that x cannot equal 0 because I can't divide by 0. And if I follow that through, even here, x squared again cannot equal 0. So my domain, all real numbers, x cannot equal 0. And for g composed with g of x, let's look at 4x plus 5. X there could be anything, so that would be all real numbers there. Then when I plug it in, multiply by 4, add 5. I'm still not limited by any values of x, so domain, all real numbers. Let's look at one more example and an application of compositions. Let's suppose that my starting wage for my first part-time job was $6 an hour. All employees get a 5% raise after 6 months, and I was given an additional raise of 75 cents per hour as a reward for my outstanding work. All right, let's find my new hourly wage if the 5% raise is applied before the 75-cent raise. Now, at first, you might not see how compositions are applied here, but we'll look at that in a little bit. So I started out with $6 per hour, and then in addition to that, I get 5% raise, so that'd be 5% of $6, so 0.05 times 6 would bring me up to $6.30 per hour. Then, after that, a 75% raise was applied. So then the $6.30 plus the additional 75 cents would bring me up to $7.05 per hour. Now let's look at the other order. Let's suppose that we first get the 75-cent raise. So that's a flat fee, raising me up to $6.75 per hour. And then getting 5% on top of that, so $6.75 plus 5% of the $6.75. And if we add that together, we get, it looks like it'd round to $7.09. So you can see 4 cents more per hour if we apply the 75-cent raise first. Well, let's look at this in general. Do you think it'd always be 4 cents difference? Would it make a difference how much I started out making? Well, let's look if I have an unknown starting wage of W. So instead of 6 here, we're going to say W. plus W times 0.05. And let's simplify this as we go. W plus W times 0.05, well, that's 1W plus 0.05W. So that gives me 1.05W. So since we're looking at functions and compositions, I'm going to let's let f of x represent the 5% raise, which we could write as the 1.05W. Then let's let g of x represent the 75-cent raise. So then g of x, whoops, and actually, you know what, I should have this be W because I'm using W for the starting wage. So let's say g of W is our initial wage plus the 75 cents. So if we look at using these two functions, and if we look at applying the 5% raise first, that would be f of w, and then composing that with function g. So that would be g of f of w would be representing the 5% raise first. Versus if we did a 75-cent raise first, we'd want to do g of w first, and then compose that with function f. Well, let's see what we get for these. G of f of w would be g of 1.05w. And then if I look at function g, it says to take the input and add 75 cents to it. Well, our input is now 1.05w plus the 75 cents. Then if we start with, let's do f of g of x, or g of w now. So starting with g of w, or the 75-cent raise first. Then we look at function f, and f says to take 1.5 times the input, which would be the w plus 0.75. And we'd end up needing to distribute that 1.05 to the w and to the 75 cents. And 1.05 times 75 cents is about 0.79. So you can see in both of these we have the 1.05W is the same, but then there's always a difference of 4 cents between the 75 cents and the 79 cents. So it should make sense that we'd want to apply the 75-cent raise first because I get the 5% raise on top of that extra as well, versus the other way around, only getting 5% on the initial cost and then the 75 cents on top of that. And our composition shows us that no matter what W is, the difference between applying in the order that we apply them will always just be a 4-cent difference. And that concludes our lesson, section 3.3, performing function operations and composition. Thank you.